Thank you. Yeah, thanks for joining my presentation, Profiling Request Latency with Critical Path Analysis. My name is Felix Geisendörfer. I work at Datadog, and I have a question for you. Do you like fast software? Raise your hands if you like fast software. I think this is all the hands. Maybe some hands were not up. I'd be curious about your villain origin story later on and how you came to hate fast software. But the rest of you, I think you're in the right room and you made some good choices leading up to this, because Go is a really good choice for writing fast software. Go is a compiled language that gives you optimized machine code from your programs. It ships with a high-performance runtime that facilitates the execution of your programs. And it's a very productive language, so you can mostly focus on just writing the code you need to do. It's really suited for team environments where many engineers are working together. And last but not least, one of Go's superpowers is that it's very observable out of the box. The runtime really has a lot of diagnostic tools, such as pprof and the execution tracer that Bill Kennedy was just talking about, but also the runtime metrics. So when you do hit an issue with performance in Go programs, you have a large number of tools to use to solve your problem. And in fact, these tools are so good that you can actually use them in a production environment. They have very low overhead, so typically 1% to 2% or even less, depending on what you're using. So you can actually profile your code in production whenever you have an issue and figure out what's happening. And since I work on continuous profiling, I also have to ask, how many of you here have profiled your Go code in production in the past? Okay, wow, that's maybe half, 30–40% of the room. Definitely not as many people as those raising their hands for liking fast software. If I had to guess, maybe most of the people who don't profile but like fast software maybe are just happy with the performance of their Go programs just out of the get-go, because maybe the database or other layers of the system or the bottleneck and the Go stuff just really works well. But I also think that some people might have actually use for profiling, but don't reach for it because it can be a little intimidating and difficult to use. So if you've never used profiling before and you look at a flame graph for the first time, it's kind of difficult to orient yourself. Like, what does good look like? What does bad look like? What should you pay attention to? And if you do decide to go after something that you think is bad, what's going to be the impact of that? And to give it a little bit more specific example, I brought you a very simple mutex contention profile from a production service here, where we can see that this service was experiencing mutex contention in a logging library that was probably using a mutex for avoiding like the interleaving of messages being written out or something like that. And so that's probably a bad thing. But we don't quite know how much it matters for the reason that the stack trace feels a little incomplete because this is a Go routine that was created by another Go routine. And this stack trace has very little context about what was sort of the activity leading up to this Go routine being created and how this Go routine is actually sitting in the application. This could be some background activity. This could be something that's really critical to the user experience. And it's a little difficult to tease out here. Even if we do determine where this fits into our program story, the question still is, how bad is this? And so one number you can see here is that the total amount of mutex contention that was happening at this stack trace was about 439 seconds. And I can tell you that this is a delta profile of a 60-second period. So this is more mutex contention time than wall time has elapsed. What this tells us that at any given point in time, multiple Go routines must have been mutex contended. So that sounds pretty bad, but yeah, this is probably worth going after, but you still don't know how bad it is. You don't know how many Go routines were involved in this. It could be 1,000, it could be 100,000, and you don't know what the average contention period was. You don't know the distribution of those contentions, how many times each Go routine was contended. You really don't know how it impacted the user experience. And this is what I would like to change in the future. I would really like to have profiling tools that can help us to understand how does stuff like mutex contention impact the P99 latency of our requests. Specifically, also, I want to know how much the CPU usage plays into it, how much channel operations play into it, how much scheduling latency plays into it, garbage collection, system calls, even sleep. You might have a program that sleeps to retry an operation. And last but not least, also networking. Even so, for networking, my colleague Hannah is going to give a really good presentation on distributed tracing after the break. And if you have a networking-related latency problem, you probably want to chase down which downstream service is actually causing that, and then do the analysis on the sort of Go internal level on that service, if it happens to be a Go service. But yeah, I would really like the ability to take profiling data and contextualize it in terms of request latency. And the question is, how could we do this? First of all, we need a really good data source, and it turns out we have one with the execution tracer that Bill Kennedy was talking about. What the execution tracer does under the hood is it basically traces the scheduler as one of the things it does. And the scheduler is responsible for orchestrating your Go routines transitioning between different states. At any given time, a Go routine can be running on a CPU core. And actually, in Bill Kennedy's presentation, that was all the rectangles you saw was Go routines running on a CPU core. But a Go routine can also block and wait on something like a channel receive operation on a mutex contention. And it can also be in a runnable state, which means it's actually ready to run, but the scheduler hasn't gotten around yet to schedule it yet, or the scheduler is currently overwhelmed with too many Go routines that are trying to run. And so you're basically experiencing scheduling latency. And yeah, the execution tracer can basically create events for all of the transitions between these states and give you stack traces for them. So you can really draw a complete picture of what all your Go routines are doing over time, with essentially nothing missing. With all the other profile types, you have to kind of pivot between different profile types and kind of stitch it together in your head. The execution tracer has it all in one place. One way to look at it is through the text output format that's available. GoTool trace has a flag called -d equals parsed, which gives you a textual output of what goes into a trace. And what you can see here is you have a Go routine with the ID 2 that's going through 3 transitions. The first one it goes from a running into a waiting state because it's blocked on a channel receive operation. The second state transition is going from waiting to runnable. And what we can also see here that the Go routine ID 1 is actually the one waking us up through a channel send operation. And last but not least, here we see the scheduler actually transitioning this Go routine from the runnable state into the running state. So this is a pretty useful way to look at it, but it's a little tedious to analyze. And well, AI is a big topic, so obvious question is, now that you have text output, can you feed it into a language model? And the answer is actually yes. Like, I've played around with this a little bit. In some cases, it provides some useful insights. But one problem is data volumes. Like you saw Bill Kennedy's presentation where a short program run already produced 1 megabyte of data. I did the math, 1 megabyte of data for a trace turns in about 40 million tokens. And that is larger than the context sizes of the state-of-the-art models right now. And it's also kind of a cost problem. It's sort of, we collect this data in production at my company, and at the volumes we collect it at for just a single host, feeding all of it into an LLM to analyze, would cost about $1 million a month, which seems a little pricey. And so, yeah. Let's not do that. We probably need to slice and dice this data into a meaningful way before, and then we can decide what to do with it, and AI being maybe one of those things. In terms of slicing and dicing the data, the traditional ways is to use our eyeballs and to our ability to do pattern matching. So we can use the GoTool trace UI to basically look at all of this and be like, oh, this looks really interesting. I should zoom in there and maybe I can find some problem to solve. But it can be a little difficult to use when you're not working on like a single benchmark or something, because you essentially see the interleaved execution of all the Go routines in your program. And if this is a production program that's serving a lot of requests, all of it is sort of bunched together. And it's a little bit more difficult to figure out what individual Go routines or requests are doing. Perhaps more importantly, you have no idea on sort of what Go routines are doing off CPU. This is only showing you on CPU. Like when a Go routine is mutex contented, there's ways to get it even in this view, but it's very tedious. You can't use your eyeballs to get a good picture from it. So the first thing to do to make this more manageable is to basically add request annotations, where you essentially tell the execution tracer what you consider to be a request in your system and where it starts and where it ends. And the way you can do that is the runtime trace package as an API to create a new task, to basically say this Go routine is now doing an HTTP request. And you can then defer the ending of that task when that HTTP request is done. And you can also attach any metadata that you might want to have about that request, so you can later on understand what request was it, for what endpoint was it. In this case, which is simply locking the whole request URL. And once you have that, the Go tool trace actually has a section. It was one of those links that Bill Kennedy thinks somebody should do a talk on at some point, that you can click on to get like all the tasks and see what they're doing. But again, the problem when you do that is you're only going to see the on CPU time. And CPU profiling is typically good enough to deal with that. So what we really want to get after is the off CPU time, and we need a viewer for that. So at Datadog, we built a viewer where you can use your eyeballs to also understand the off CPU time. So what we're seeing here is a single HTTP request that took about 110 milliseconds. And you see all the Go routines that were either directly involved in that request, as in they were the Go routine that started and ended the request, or they somehow are Go routines that communicated with that Go routine. So we're pulling in a bunch of those and showing you what they're doing. But you'd think that this answers all our questions, but it still kind of doesn't. Like, it gives us an idea that there's mutex contention here, but how much is it and how much does it matter? Because we're actually experiencing, again, the situation where we have more mutex contention time than wall time being elapsed. So this request was 110 milliseconds, but there's about 214 milliseconds of total mutex contention in the related Go routines. So what does it mean? Like, how can we actually prioritize what to do here? And so one thing you can do also with Go tool trace, you can start clicking around and trying to go deeper and really understanding what's actually important. And the way you can do that is you can click on the main gRPC Go routine that is starting the request and ask what was this spending most of its time on. Turns out it was blocked on a select statement. So it was waiting. So now the question is, who woke us up, which Go routine, and what was that Go routine doing before? That's the kind of analysis we want to do. So we can do that by keeping clicking around. Then we get to a Go routine that is blocked on a sync.wait group, and we again ask the question, who unblocked us? And eventually we get to this Go routine from this error group that was really the culprit, and like that's what we were really waiting on. And as we can see, this was mostly CPU bound. This Go routine, like this whole lane, is essentially in the blue color for running time for on CPU. And there's actually only a tiny little bit of mutex contention here. So we can click on these events, get stack traces, figure out what's going on. But the mutex contention time here is actually just 2 milliseconds. So only 2 milliseconds of mutex contention actually contributed to this request. And this is why it's so important to contextualize and understand how this all fits together. If we wanted to now answer the question, why are all these other unrelated Go routines shown here? The reason for that is, once you have mutex contention, you know you were slowed down by somebody else holding the mutex. But what you want to know is, what was that other thing doing? So you want to see the other side of it. And in this case, we actually have to go down a list of Go routines waiting on this mutex. There was kind of a queue forming, so that we see that there was another Go routine that was also waiting on the mutex, another one also waiting on the mutex, and all of those had to wake up until we could get unblocked. And this here is actually the critical section where some Go routine was holding that mutex. But again, the most important takeaway here was this mutex contention is very minor compared to the total request latency, and the other mutex contention here on these other Go routines, maybe it impacted other requests, but not this particular one. So what we just did manually, it would be nice to actually do this in an automated fashion. And this technique of like going backwards to figure out what's on the critical path is actually called critical path analysis. And this technique was developed as part of the Manhattan project and contributed to the success of it. And what it basically is given a project that can be divided into sub-projects that can be executed sometimes in parallel, sometimes there's dependencies between sub-projects. The question is, which of these sub-projects are on your critical path and need to be accelerated to accelerate the overall project schedule? And one way to define that is by determining the path of the longest stretch of dependent activities. So here we have a project where you first need to do sub-project A, then you can do B and C in parallel, and then you can do D after B and C are done. And so the longest path through here leads you through C, because C is a 4-month sub-project and B is a 3-month sub-project. In other words, if you made sub-project B faster, great, you've done something nice, but the overall project cannot complete faster, because B is what's considered subcritical here. It has about 1 month of slack before it would actually become critical and would be worth your attention. For now, you would only want to focus your activities on C. And as I said, we kind of did critical path analysis already, because one algorithm for actually getting the critical path is going backwards. You start at the end of the activity, then you ask what needs to complete for the end to be reached. That's activity D. And then you ask, now I have B and C, which of these activities is the last one to complete? And that's the one I'm going to follow. We're going to look at more examples of this now. But basically, I asked myself, this technique I found out from work done by Google and Uber, who actually did it in the context of distributed tracing. They applied this critical path analysis there. And I thought to myself that the execution tracing data we have is actually very similar structurally. And I was wondering if we could apply the same ideas. And so I'll show you how far I got with this so far. Here we see a single Go routine. And if we want to do this analysis, it would be very simple. You would start at timestamp 1000, go backwards to timestamp 0. And along the path, we might have some CPU samples that allow us to break down the latency, the activity of the on-CPU time of this program. And here we might just have 10 CPU samples. This might not be statistically significant enough yet to really focus on which CPU time is significant and which code to change. So we could repeat this for many requests and aggregate the results together. But yeah, for this trivial example, it obviously works. Where it gets interesting is once we get concurrency. So here we have a Go routine G1 that is launching another Go routine G2, and then it's waiting for the task delegated to this child Go routine to complete. And critical path analysis here would be the process of going backwards from timestamp 1000 to timestamp 500, then realizing, oh, G1 was waiting on something. What was it waiting on? Well, G2, because G2 is unblocking us. So we want to understand what was G2 doing, because if we can make that faster, then our whole request can finish faster. That's why this is the right analysis to do here. And eventually, once we're running out of G2, then we pop back up to the G1 segment in the beginning. Where it gets really interesting is when you get a schedule that includes concurrency. So here we have Go routine 1 spawning 2 child Go routines. And then you can imagine that there's a for loop where the G1 Go routine is waiting for the results from each of those Go routines. So that's why there's a little wake up here for G2 waking up G1 around the timestamp 500. And then G3 finally waking us up at 650. And the critical path analysis here again is going backwards and asking what is the last activity to finish. In this case, it's Go routine number 3. And we want to know what that's doing in order to make our program faster. Go routine 2 is totally irrelevant here, because if we actually made Go routine 2 faster and G3 is still our bottleneck, it doesn't matter. So that's why it's not on the critical path at all. It is subcritical, and we need to focus on G3. And once we have a critical path, we're guaranteed that making anything on the critical path faster will make our program faster as well. But up to a point where there might be some other background activity, then we have 2 bottlenecks where it gets trickier. This also works for other concurrency patterns. Like here you have a worker pattern where G1 is actually waking up a worker Go routine, G2, through maybe a channel send operation. Then G2 does some work for us and eventually wakes us up again. We're waiting for that work to complete. So that works. But there's some trouble in paradise. Workers can be busy and channels can be buffered. And when that happens, we might want to delegate some work from G1 to G2 while G2 is currently busy. But we have a buffer channel, there's some room for it, so our message ends up in the buffer channel. But that means that the execution tracer, which is our data source, doesn't actually capture an event for that. And so this little gray arrow going down at timestamp 200, we don't actually have this in our data. And so if we applied the technique as presented so far, we would be doing the analysis going backwards from timestamp 1000 to timestamp 500, pop into G2, and there go from 500, well, all the way back, because we have no return path to G1, which actually means we don't have a critical path. We don't know how to find it. And the answer for this scenario is to actually set a time limit. So we know how long G1 was waiting for G2, and we consider that to be the limiting period for when we're going to explore the G2 path, and then pop back up automatically. But as you do adding like these heuristics to the algorithm, you get into more trouble. Like if we just added this one heuristic, and we looked at the previous example again, we would have actually regressed on it, because we would set a time limit at timestamp 650 as we go backwards, attribute a little bit of time to G3, then pop back up to G1, and then actually find a critical path that goes through G2 as well, which as we know is already incorrect. Making G2 faster here is not correct. So the solution to this in the algorithm is to basically only set a time limit if there's no return path to the Go routine that you're trying to get to eventually, like the initial Go routine, or if there's a mutex wake up. And I'll explain the mutex wake up in a second, because it's kind of an important exception here. This example, which I call full path, kind of looks like a work delegation pattern, where you have a worker Go routine that's receiving some work from G1 to G2, and then G1 is waiting on G2. But that's not actually what's happening here. G1 and G2 happen to be completely separate requests that are executing just concurrently. And they share like some data structures. So there's a mutex around it, and there's contention. And it just happens to be so that G1 initially holds up G2, so G2 gets mutex contended on G1, and then vice versa later on in the request, because they hold the same mutex multiple times, G1 actually has to wait on G2. And this would send us also down a false path, because we would go from timestamp 1000 to 800, pop into goroutine 2, and then stay on goroutine 2 until timestamp 250, and then pop back out, which actually means we would attribute a whole bunch of time spent on another request's critical path to our critical path, which, yeah, is not what we want. We want this analysis to be more precise than that. So one way to solve that is through looking at the stack traces and using those to determine if there is mutex contention. But that is not fully sound, because we cannot know all the stack traces that would indicate a contention, because you can also model mutexes with channels. So we have some ideas for additional heuristics to use, for example, when there's overlapping tasks. Like if we go into a Go routine that is executing another task already, we're probably in a mutual contention scenario. We also don't have the lost edges from the blocking send operations. And there could even be lost edges because of Go routines waking each other up through mechanisms that are hidden from the scheduler, such as like maybe Unix pipes. But I think perfection is the enemy of good here, because we have some reason to believe that this can still work out. And the reason is we've started analyzing this for a lot of concurrency patterns that we think Go programs will experience in practice. And we're pretty happy overall with the results. We think that in most of the cases, it's actually going to work. And perhaps more importantly, we're starting to throw this as real-world data, including the example that I just showed you earlier. And in most of these cases, we're seeing that the algorithm either refuses to produce a path, or it produces the exact same path that a human would produce. So we think this kind of analysis can really play out well in production. And yeah, in this example, if we zoom in, we can also see that we now actually get some interesting stuff on our critical paths. There was a little bit of scheduling latency here. Here it doesn't matter so much. But in practice, we find a lot of programs are suffering bursts of scheduling latency. Maybe you're spawning Go routines in a loop, or maybe there's like a burst of requests arriving. And it's really difficult to like communicate scheduling latency. Like there's a metric for that in the Go runtime, but communicate to engineering teams how much they should care about this for their tail latencies, and think about different patterns of work distribution or increasing capacity or other measures they could take. So this is very nice. And last, I want to address the stack trace situation. So I mentioned earlier that one issue is that the stack traces can feel a little incomplete sometimes, because when you launch a new Go routine, you're missing some context from the ancestry of Go routines. And I think one thing we can do once we have a critical path is we can actually stitch some artificial stack traces together that will help people to understand the context of their operations much better. So for example, here we can stitch the wait stack 1 together with run stack 2, or wait stack 1 with wait stack 2 and run stack 3, and so on, which would ultimately give us a picture like this, which would be a flame chart showing us what this request was doing over time. And when the main Go routine is waiting on something, we show you the stack trace of that. And below that, we show you what's on the critical path. Or if there's another layer of waiting, there's another stack trace, and so on. And so like mutex contention would actually show up as like several mutex unlock operations. And finally below, you would see what you're really waiting on. So I think that could be pretty useful. And once you have your data in this format, it could also be aggregated and turned into profiles. So you could do this for many requests and see what a profile for a P50 latency request would look like versus a P99 request, and really get a good idea of what's worth your attention and how much leverage you're going to get by going after these problems. Last but not least, we love open source at Datadog. I actually hope to open source all of this work and make it available to the community. Up until now, we've already contributed a bunch of other things back. In particular, over a year ago, my colleague Nick and I helped to make the execution tracer much lower overhead. It used to be 10 to 20%, and it's now down to 1 to 2%. So this was a critical part of like getting to the point now where we can do this advanced data analysis. And we're also in the process of contributing some code to make it easier to work with execution traces. there's a very nice library to actually takes the data from the execution tracer and process it in Go, but there was no way to actually mock that data and like create test cases and stuff. So this is what we're contributing back right now. And all the diagrams from the Go routines you saw were actually created using test data that was created with the CL, which hopefully will be merged soon. I think that's all I had for today. So I want to thank you. I want to thank the organizers for putting this event together. I want to thank my colleagues at Datadog, especially Nick Ripley, who I work with on all the Go stuff. I want to thank the Go team for all their reviews and discussions around all of these runtime diagnostic topics, especially Michael Nichek, Michael Brett, Jerry, Keith. Everybody on the Go team has really been super helpful with things in the past. And as a last call to action, if you find this useful and you have use cases for analysis like this, please come to me afterwards, share your situation. Maybe you'd be interested in trying out early versions of this. Or if you don't want to talk, maybe just follow updates on Blue Sky and X in the future. So thank you.